Hello, this is Mrs. Pullen for Algebra 2, Lesson 11.02 on graphs of logarithms. So in the first exercise, they ask you to graph log base 3 of x, and we know a log is the inverse of an exponential function. So let's start by graphing y equals 3 raised to the x, and yes, you can use your GeoGebra to graph it, but I'm just going to graph this by hand. So I'm going to substitute negative 2 in for x. That's 3 to the negative 2. And that's equivalent, hold on, let me just get the right tool out. That's equivalent, 3 to the negative 2 is the same thing as 1/9. I substitute negative 1 in for x. That's 3 to the negative 1, which is 1/3. 3 to the 0 is 1. 3 to the first is 3. And 3 to the second is 9. So let's go ahead and graph it. Each box is worth 1, so 1, 2, 3, 4, 5. And this would be negative 3. This would be 4, 5. And this would be negative 3. So you should always show the scale. And let's start graphing this. So negative 2, 1/9. 1/9 is like 0.11, so it's over here. 1/3 is negative 1, 1/3 is here. And then it's 0, 1, 1, 3, and 2, 9. And we're going to make a nice smooth curve. So exponential functions have horizontal asymptotes. In this case, the horizontal asymptote is the x-axis, y equals 0. Then when we're taking the inverse of the function, which creates the log function, you switch your x and y. So this would be 1/9 and negative 2, 1/3 and negative 1. 1 and 0, 3 and 1, and 9 and 2. And let's go ahead and graph this. So this would be 1/9 and negative 2, and 1/3 and negative 1, and 1, 0, and 3, 1, and 9, 2. So that's, and it's nice smooth curve. And these functions are inverses of each other, and you can get the log function by reflecting it over the line y equals x. You're literally switching your x and y. So we're going to compare the domain and range of the exponential function y equals 3 raised to the x and the log function y equals log base 3 of x. So the domain of the function is not all reals. Oh, for exponential functions, it's all reals. So this graph in the red, you can put in any x value. So it's going from negative infinity to infinity. Your range, however, for the graph in red, the lowest y value approaches 0 but has to be greater than 0. So it's soft bracket because you're not including 0 all the way to infinity. And as we discussed a moment ago, the asymptote is y equals 0. So it's that guideline, this function, as long as it's in the form y equals something raised to the x with no adding or subtracting of a constant, the asymptote would be y equals 0. The domain of a log function is different. That's the one in blue. You can't actually cross the line x equals 0. So the function approaches the y-axis without crossing it. So the domain is 0 to infinity. The range, however, it goes infinitely far to the negative infinity, and eventually it will reach infinity. So it's all reals. The asymptote is actually the y-axis, and so it's x equals 0. So as we just graphed exercise 1 manually, but you can use GeoGebra or any calculated graph. And we're going to graph the common log, which has a base of 10, so log base 10 of x, and we're just going to sketch that graph on this grid, and we're going to label the x-intercept and state the domain and range of that function. So if you go into GeoGebra, and we're going to actually type that function in, and to do it, you actually have to be in f of x, and you can see, whoop, now I have to find where it is again. Hold on. So it's, let me hide this so we have a better sight of it. So you would just type this and type in the x for the function and hit enter. And we get the function. Oh, this is annoying. And I'm just going to scrunch this a little bit. And if I change the scale and get a close-up view, what you should start seeing is the graph approaches it, and it's just a limitation. It actually never crosses the x-axis, but it's helpful to actually get a table of values. The asymptote, again, is going to be x equals 0. And so we're going to go ahead and get a table of values. And why don't we go from -2 to 20? And so we see the different values of the function, and we see that the graph has that at 0, it says -infinity. It's really undefined there, and that's where you would put the asymptote. All functions in the form log base b of x are going to pass through the point 1, 0, and we see these decimal values, and what you should see at 10, the function's equal to 1. So those are some key features of this graph. So to graph the asymptote, your input, to get the asymptote, you would just take your input and set it equal to 0. And we're going to make a dashed line. I'm going to make it in green. And that's labeled the equation of the asymptote. And it's passing through the point, let's do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's passing through 1, 0, and then it also hits 10, 1. And at values between 0, 1, you're going to see that it's negative. So if I wanted to go ahead and see a value, notice at -4, just want to see this point over here. So at the point 0.05, it's -1.5. So we can actually kind of graph that. So the function looks something like this, with arrows on both ends. So between 0 and 1, it's going to be below the x-axis. It crosses at the x-intercept of 1, 0, and at 10 it approaches 1. And that's the common log. So using technology, we're going to graph the function y equals log base 2 x plus 4 plus 2. So we're going to do this in the graphing calculator again. So the first thing they want you to do is get the equation of the asymptote. So you're going to take your input to the function and set it equal to 0 to get the asymptote. So x plus 4, you're going to set equal to 0, and the asymptote is going to become x equals -4. And I'm going to graph that in red. So we normally graph it with a dashed line. And make sure to label. That's really important. The domain of the function is going to be greater than -4 as long as it's in this form. And so that would be -4 soft bracket to infinity. And the range is going to be all reals. And there are a couple of ways to get the x-intercept, but for our purposes, we're going to actually graph it to find it. Okay, so we're going to change this function, so let's clear. And we're going to put in this equation. So you would go into the function again. And in this case, instead of using log base 10 of x, you use to the one just to the right. And there's a little subscript button, which may be hard to see here, but you would just put in the subscript. Make sure you do that, otherwise you'll get an incorrect answer. X plus 4, go, whoop, x plus 4, go out of that parentheses, plus 2, and hit enter. And we want to change that window a bit. So we can see the function a little bit better. You can't actually see the asymptote. It's a guideline, so the function approaches it without ever crossing it. And let's see if we can get a better hold of what that function looks like here. More of a close-up version. Play around with it a bit. We're actually going to get a table of values in a moment. I just want to expand my y-axis and get a better close-up. At the same time, make my x-axis smaller. Well, we're getting there. Scrunch up my x-axis a bit. I'm getting more. This is a better look to that function. Okay, so that's our log function, and the asymptote is right here. And so let's get some values. Table of values. So we're going to go from -5, and let's go out to 30. Because I think I give you up to 30. On the graph. So we can actually, before I was talking about the x-intercept, we can actually get the x-intercept from clicking on the function. Okay, let's try this again. Tools, I want to find the x-intercept. I found it before a different way. So I'll show it to you a different way because but you should be able to find it just from the graph. So one thing you can do to find it is you could just go y equals 0. And we can find the point of intersection. So it intersects at -3.75, 0. So that is the x-intercept. I found it algebraically in the notes. Okay, so let's write that down. So one way of getting the x-intercept is to set the original, create a second equation, y equals 0, and then find the point of intersection, which we found as -3.75, 0. So when you're graphing, you're going to use that table as I showed before, right? Or I didn't show it on this one, so we're going to do this now. Actually, I guess I did. So we're going to graph I graphed the table from -5. Notice there's nothing at -5 because the function does not exist there. And you're going to just pull off, and my recommendation is to pull off the whole numbers and graph those. So we're going to create a table from this on our paper: -3, -4 undefined, -3, 2, -2, 3, 0, 4, 4, 5. As you see, we're just pulling off the whole numbers to make our lives easier when we're graphing. 12, 6, and 28, 7. So let's create this from our table. Let me just get my notes out so it's a little easier. So here's X, here's Y, and at -4 it's undefined. That's where you're going to put your asymptote. We know that we are going to graph -2, 3 because it was a whole number. 0, 4, 4, 5, 12, 6, and 28, 7. So you want to have at least 5 points excluding the y-intercept when you're graphing. So let's graph these values. So it's -2, 3, 0, 4, 4, 5, 12, 6, and 28, 7. And we're going to make a nice smooth curve. Now, the other thing that I want to graph before I make that curve is that x-intercept of -3.750, because it helps us. We know it's going to go below the x-axis there. And so let's make that nice smooth curve with arrows on both ends. Okay, it has to pass through the x-axis, and that's your log curve using technology. Okay. Just a couple of other problems. So the last problem that we're going to go over in this video is example 4. So determine the domain of the function y equals log base 2 of 3x minus 4 and state your answer in set builder notation. Okay, so to get the domain, what you're going to do is you're going to set your input greater than or equal, just greater than 0. So let me actually write that as a note. So you're going to take the input or the argument to the function. That's the argument, or it's called the argument, or the input. And you're going to set that greater than, because it actually can't hit that value. It's undefined at that value. And you're going to set it greater than 0. So 3x minus 4 is greater than 0. 3x is greater than 4. X is greater than 4/3. So the domain of this function in set builder notation is x such that x is greater than 4/3. It can't even be equal to 4/3 because log of 0 is undefined. In interval notation, it would be 4/3 with a soft bracket to infinity. In any case, I hope this video was helpful, and I will see you tomorrow.